So most people are going between A and B. Turns out it's actually C. It's the same area under the curve. So you would get the same result if it's a big force over a short amount of time or a smaller force over a greater amount of time. The area under the curve is the same. Okay, so they have the same change in momentum. If they have the same mass, that must mean they have the same final velocity. Okay. So again, instead of actually being able to use calculus to calculate the change in momentum, we'll think about this as the average force over the same amount of time, though. So impulse, J, area under the curve, force times time. The units are newtons times seconds, but a newton times a second is the same thing as a kilogram meter per second. There's no other units, it's just newton seconds or kilogram meter per second, same exact thing. Okay. And it is a vector. So I gave you the whole long list of how to actually use it, all the different quantities that we had before. Okay, good. So this is like a brand new tool that we have today. Here are some typical momentum values. So a falling raindrop, really small mass, kind of a small speed actually relative to the other ones. 10 to the minus 4 kilogram meters per second. A bullet, not very much mass, but moving really fast, has 2 kilogram meters per second. A baseball, if you watched any baseball the last 2 days for the playoffs, a lot bigger mass than a bullet, a lot slower, but more momentum, right? It's because it's mass times velocity. So a baseball actually has more momentum than a bullet. A running person, the mass is going up but not moving as fast, 200 kilogram meters per second. Just to give you an idea what these things look like. Car on a highway has a whole bunch, right? Moving fast and has a lot of mass, relatively speaking. So momentum, mass times velocity. Okay, good. So this is similar to homework 5, which I'll be putting up a little bit later today. It won't be due for a while, but I'm going to get it up there anyway. This is similar to 9.7, which will be on homework 5. So we've got a 2 kilogram object moving to the right at 0.5 meters per second, experiences this force. What are the object's speed and direction after the force ends? So let's actually work this one out. Okay. So we know the mass, 2 kilograms. And moving to the right with 0.5 meters per second. Experiences this force. So we've got 2 newtons for half a second, right? Just from the graph. And then what we want to know is what are the object's speed and direction after the force ends? Okay, so we've got all of these different ways we can take a look at this. This is the impulse theorem up here. Here's a clue to use that. We've got mass, velocity, force, and time. So if you take force times time, that's equal to mv final minus mv initial. This is all in the x direction, so I'm not writing the vector sign above it. It's just all in the x direction. Okay, so again, the clue to use this was all the information that we're given. I write it out, and now what I'm trying to figure out is the final velocity. So I've got to do a little bit of work here. I've got to get that by itself right in the equation. So I can add mv initial to both sides. And then if I add that to the right side, it adds up to 0. And then I've got to divide both sides by the mass. And that'll give me the final speed. Okay. So I could have figured out the acceleration from the graph, and then once I had the acceleration, I could use kinematics to figure out the final speed. You could do it that way. On the test, I won't tell you, make sure you do it one way or another. It's totally up to you how to do it. This way maybe it's just a little bit easier. And then we could put the actual values in here. So we have 2 newtons for a half a second plus 2 kilograms times 0.5 meters per second divided by the mass, which is 2 kilograms. So this would be 1 Newton second plus 1 kilogram meter per second. Remember, those are the same things, though, divided by 2 kilograms. So it looks like we end up with 1 meter per second. Right, the kilograms cancel out. So we go from 0.5 up to 1. So we're moving towards the right. So why is a Newton second the same thing? Newton times second. A Newton is a kilogram meter per second squared. That's the Newton part times a second. And then you get the same thing. Kilogram meter per second. Okay. Very good. All right, any questions on that one? Good, so we got this fancy new impulse relationship we could work with. We saved a lot of time by not having to figure out the acceleration, and then once we got that, we used kinematics, which equation am I going to use? Here we could just do it in one step. Okay, good. Any questions on that one? All right, very good. So there's it kind of worked out for you a little bit. Ooh. So a force pushes the cart for 1 second starting from rest. To achieve the same speed with the force half as big, the force would need to push for a quarter of a second, half a second, 1, 2, or 4 seconds. So you have a given force, it pushes for 1 second starting from rest. To achieve the same final speed with the force half as big, how long would you have to push? So it's a voting one. Oh, thanks, Rick. Okay, let's start over. A force pushes the cart for 1 second starting from rest. To achieve the same speed with the force half as big, the force would need to push for, quarter of as long, all the way up to 4 times as long. Okay, and again, this is a voting one for us. Okay, good. Excellent. Good, good. So if it was, we want to get the same speed, but we cut the force down, we got to make the time bigger, right? Let's see if that's on here. No. So force times time, that gives you the change in momentum. So if you want to have the same change in momentum, if you cut the force in half, you'd have to have the time be twice as big to have the same change in momentum. I believe that's what they're saying. We want to have the same change in momentum because that will give us the same speed. Okay? So force times time, change in momentum. Make the force half as big, you have to make the time twice as big to have the same change in momentum. Okay, good. So maybe let's take a look at this one and we'll make this our last one for the day. Ball, mass 0.25, rolling to the right at 1.3, strikes a wall, rebounds to the left at 1.1. What is the change in the ball's momentum? And then what is the impulse delivered to it by the wall? So this is a trick question, really. What is the change in momentum? And then what is the impulse? They're the same thing. If you're not in physics, you might think impulse is force or something like that. But impulse, change in momentum, same thing. So they're just asking the same question twice. They're just calling it something different. Okay, so what we want to do is figure out the change in momentum. Okay, so one key thing is we're moving this way. The mass is 0.25 kilograms, moving at 1.3 meters per second. Now when you hit the wall and you head back the other way, at 1.1, you've got to make sure that you put the negative sign there, right? If you're saying this is the positive direction, this has to be the negative direction. Okay, so the change in momentum is the final momentum minus the initial momentum. The final momentum is mv final minus mv initial. And then we have everything. This is the initial speed, this is the final speed. So let's actually put these numbers in. 0.25 times minus 1.1, and then minus 0.25 times 1.3, 0.6 maybe. .4, 1.2, 0.6. I think that's what I get, 0.6 with the minus sign. So it's negative because the thing's changing direction. The ball was moving to the right, so the force must have been back to the left for it to move this way. It's moving this way, now it's moving that way. You know, what made it change its momentum? Because its momentum changed. It was going one way, now it's going back the other way. Momentum, you have to put the direction because it's a vector. So the momentum has changed. It was this way, now it's that way. The outside force came in from the wall. If we knew how long this was in contact with the wall, we could figure out the average force on the ball. You might be able to make a nice video of it, look at how long it's actually in contact with the wall, measure the time. Knowing the change in momentum and the time, you could figure out the average force on this ball with some nice photography. Okay, and again, the negative sign just means the force, as you can see, let me show you the picture, is back to the left, in the same direction as the change in momentum. Okay, great. Any questions on this one? Okay, so that's all for today. What you have coming up is this homework 4 that's due on Monday over the end of chapter 5. So make sure that you take a look at it. Any questions, send me an email. If you're in group A, I'll see you tomorrow. If not, you don't have a lab this week if you're in group B. All right, no questions? All right, excellent. See you soon or next week, depending on